Version which happens in SN2, which is also known, which has a fancy name of Walden inversion. It happens because the attack of nucleophile and the departure of leaving group take place simultaneously, and for that the nucleophile has to approach the substrate from the side which is opposite to the leaving group. Okay, so is it clear? Any doubts in this?
No doubts.
Okay, good. Yeah, and it is a bimolecular transition state. I think we did this question.
Yes, sir.
Yeah, okay. And this one?
Yes, sir.
Okay, good. These are some of the SN2 reactions, examples of SN2 reaction which we use in our very common in all the conversions which we carry out in all the chapters. Okay, so you can prepare ether, thioether. Okay. This is very important. CN. Okay.
Yes.
Yes. Okay. So I think we were at this table, right? So this table is from NCRT, and actually it is telling you what on the substrate, what should be the appropriate reagent which should be taken so that you get your desired product. Okay. You can look at the nucleophile OH minus H2O. Actually, OH minus and H2O. OH minus is stronger nucleophile, right? Why? Because it is minus. Okay. Clear?
Yes, sir.
Okay, and this was which reaction? Can you name it? It is very important.
The nucleophilic substitution action.
Yeah, it is nucleophilic. But when you substitute chloride and bromide by iodide, what was the name? Just try to recall it. Because iodides we were not able to prepare directly. That was the problem with iodides. Okay, so what we did, iodides can't be prepared by sunlight and taking I2 and alkane, because the reaction was reversible. So what we did, we prepared chloride and bromide, but we took alkane, we took chlorine and bromine. Okay, we treated them with sunlight. Okay, and that actually gave us chloride and bromide, and we took iodide. Iodide actually substituted the chloride and bromide. That was Finkelstein reaction. Okay, I hope you can recall it, right? Good. And if you take ammonia as a nucleophile, okay, what you will get? You are going to get RNH2 as the product. Okay. So what should be the reaction? How can you write it? The reaction can be written as CH3 Br you can take plus NH3 heat. Okay. And you also take some base K2CO3. Okay, or Na2CO3. So actually this is a nucleophile and this is going to attack, and the Br will act as a leaving group. So immediately you are going to get CH3 NH3 plus and Br minus. It is because the N of it was neutral. Once it attacked, it lone pair got involved in the bond formation. So it was this. Okay, and then why I told you to take the base. Okay, I asked you to take the base because sometimes it is written, sometimes it is not written. It will remove HBr from here. So CH3 NH2 you will get, or you can simply write minus H plus from the NH3 plus and Br minus. So you get your amine. This is the preparation of amine. Okay. But instead of NH3, if you take primary amine, which already has one R dash group, and it attacks another NH2, it attacks another RX. Okay, you get a secondary amine which is having two R groups. Okay, this is how the reaction happens. Is it clear?
Yes, sir.
If you take KCN, the CN minus will be the nucleophile. And if you take AG, so you end up with, suppose if you take CH3Cl, and if you react it with KCN, okay, K plus is just a spectator ion. It is not going to do anything because it has already noble gas configuration. Okay. So Cn minus is going to come and attack on this carbon. The Cl minus is going to depart as a leaving group. And the RCN which you will get in this case is CH3Cn. Clear?
Yes, sir.
And what happens with AgCN and why?
So the N attacks instead of C.
Yeah. Why? What is the reason?
So because the carbon is already bonded with this Ag group, and
Yeah.
since N is the only free group there, and which can easily attack then compared
Yeah.
to carbon, it
Yeah.
goes
Very
to
good. Yeah. So why is not the carbon bonded in this case? Because it is an ionic compound. In the case of silver, it has covalent character. So carbon and silver has some covalent bond between them. That's why the carbon is not able to attack. So who is going to attack? The nitrogen is going to attack, and the carbon nitrogen bond is going to form. So you are going to end up with an isocyanide, right? And same is the case with KNO2, potassium nitrite and silver nitrate. And tell me what kind of nucleophile is this CN minus? What is the name for this kind of
the
nucleophile?
ambident nucleophile.
Ambidentate nucleophile, yeah, correct. Same is the case with nitrite ion, the O minus is going to attack. Okay. And in the case of Ag, the O minus is involved in the bonding, so nitrogen is going to attack. Okay. And in this, it is quite clear that RCO minus is going to attack. In LiAlH4, is it clear? Lithium aluminum hydride or NaBH4? How will you think this? Li plus, right?
Yes, sir.
Aluminum is +3. Okay. And there will be 4 H minus ion, hydride ions connected to aluminum +3, and due to which it is having AlH4 minus. Okay. The overall charge will be minus, right? So this H minus is going to come out because the bond between aluminum, which is a third period element, and H is a first period element, is not very strong, and it is going to come out. And this is going to attack Rx, the delta plus of R. And the X minus will act as a leaving group. So you end up with an alkane. Okay. And if you take this kind of compound, what this compound is known as? M represent metal. Yeah. What these type of compounds are called? Yeah. This is carbon metal bond, and these are known as organometallic compound. Right?
Yes, sir.
Are you familiar with any kind of, this is a general classification, any particular kind of organometallic compound? Yeah. And that is Grignard. What is Grignard reagent? What you do, you take an alkyl halide, okay, it is liquid, and there are small pieces of magnesium available, that is known as magnesium turnings, okay. You put it in ether, okay. Ether can be diethyl ether, ethyl oxygen ethyl, okay. It acts as a solvent for dissolution because magnesium is a metal, it is solid, okay. It dissolves in ether, okay, and it reacts with, actually magnesium, you know very well that it gives loses 2 electron, okay. And RCl, how we are going to break it as R plus and Cl minus, and the 2 electron released by magnesium will be taken by the R plus, so R plus will become R minus, right? After accepting 1 electron, it will become neutral, and 1 more electron will make it minus, okay. So Mg was +2, okay, X was minus, Cl was minus, okay. So this is Mg2 plus, but the charges are not perfectly +1 -1 because there is a covalent bond which sharing, little bit of sharing it takes place, and this organometallic compound in which the carbon is bonded to magnesium is known as, what it is written, tell me quickly.
So Grignard's reagent.
Yeah, Grignard reagent. Good. So in the nucleophile is not written in the pure form, but it is, you need to understand yourself that in this the R minus is going to be the nucleophile, or R dash minus. In the RMGX it is R minus, okay. And it is not only used in this chapter but in all the subsequent chapters, okay. So this is going to attack the RX halide which you have taken, and carbon carbon bond is going to form, and you are going to end up with an alkane. Clear? Any doubts on this?
Yes, sir.
So in this actually
No,
we, yeah, so this is actually a general way to prepare new different functional groups with the help of nucleophilic substitution reaction. And now there is one more way of, so actually we did what we discussed in SN2 reaction. We were doing nucleophilic substitution bimolecular, and which occurred in which both the reactions occurred simultaneously. The attack of nucleophile and the departure of leaving group took simultaneously. That's why it was called bimolecular. That's why the 2 is there. And we have seen, because that in the transition state, everything was happening together. You can see over here. Okay, it is very crowded. And if you increase the size of the 3 groups which are actually not participating in the reaction, they are going to make the reaction difficult. Okay, so what we analyze there is that as the branching increases, as the halide changes from methyl to ethyl to isopropyl to tertiary butyl, okay, the carbon changes from primary to secondary to tertiary. There are more and more alkyl groups present on the carbon which is directly connected to halide. And that will, this is written in condensed way, but actually there are these 9 hydrogens also which will be spreading outside, and they will prevent the nucleophile, they will stop the nucleophile from coming and joining itself to the carbon containing Br. Okay, so that's the main problem. So tertiary alkyl halide never undergo SN2 reaction. Okay, it is very difficult for them, very less rate for SN2 reaction, right? Because SN2 simultaneously it happens. But does this mean that a tertiary substrate will never undergo reaction? Can it undergo substitution reaction? It cannot undergo SN2 reaction, okay? Can it undergo substitution reaction? Why it cannot undergo SN2 reaction, that is clear, I hope. Pharmacy. Clear?
Yes, sir.
Because these methyl groups have 9 hydrogen. Okay, they will be the structure will be very much crowded, very much cluttered. Okay, so the nucleophile can't come and join to the carbon atom. That's the main problem. Okay, so that's why it can't happen. SN2 can't happen, but that doesn't mean that the substitution can't happen. Substitution can happen, but it doesn't happen by SN2 mechanism, which involves simultaneous arrival of nucleophile and simultaneous departure of leaving group. Instead, it happens by another mechanism, okay, which is known as SN1 mechanism, right?
Yes, sir.
So what do you understand by the term SN1?
So substitution, nucleophilic unimolecular reaction.
Yeah, substitution nucleophilic unimolecular. Yeah. So what may be happening over here? As we know, what we expected over here is that this is tertiary, and we can't expect the nucleophile to come and attack this carbon atom because it is too bulky. Okay. So we were expecting that it may not happen at all, but the reaction happened with a significant rate. Okay. So why?
So because the cleavage and the attachment of the bond happens in the same time.
Happened at the same time?
Uh,
Yeah, in SN2 actually, yeah, Mohammed, good evening. I hope you can hear my voice. Actually, in SN2, it was happening simultaneously. The arrival of the group and the arrival of the nucleophile and the departure of the leaving group was taking place simultaneously. But that can't happen here because of these groups. Okay, they will not let the look over here, right? It is like this. So nucleophile can't come here in this case. So if you want to put one group and if you want to remove another group, either you can do them simultaneously. What are the other ways? If you consider only the sequence. Yeah, Mohammed Mamsi, tell me quickly. What could be the you don't have to tell me the exact mechanism, just tell me the sequence and how it may occur. Yeah. So one way we already discussed, in which both things happened simultaneously. Okay. The nucleophile
Sir, I
came.
think it is attachment of nucleophile and then cleavage of the CX bond.
Yeah, that could be one of the options. Yeah. That could be one of the option. The nucleophiles, suppose there are two guests, okay, which are planned, and one guest is already sitting, okay, in at your home, and another guest are about to come. Okay, so it may happen that the guests which are whose arrival was expected, they come, and the guests which were already sitting, they leave together simultaneously with, and there should be that should happen from two doors. Okay, one on this side and another on this side. So one guest which is already sitting, they are leaving, and another guest are arriving simultaneously. It is happening. Okay, so some family members are busy in saying bye to the guests which are already sitting, and some guests were already some guests are coming, and some of the family members are inviting them. Okay, yeah. So this is one way. Then that was SN2 reaction. And as Vamsi, you said that okay, the guests which were sitting, they remained seated, and the guest which was expected, that they came and they also joined. Then the guests which were expected to leave, they left. Okay, after the arrival of new guest. Okay, yeah. So this could be the sequence theoretically possible, but not possible on carbon. Not possible on sp3 carbon. Means the nucleophile can come and join the carbon atom, and later on the leaving group breaks away. Why can't it happen on sp3 carbon? Krishna and Mohammed, tell me quickly.
So because carbon is tetravalent.
Yeah, carbon is tetravalent. It can happen on silicon. It can happen. It happens. Okay, on silicon. Okay, a sulfur, where they can make more bonds, but carbon cannot make more bonds, so it is not possible that the nucleophile come and join the carbon and then leaving group goes away. Not possible. Either they should come and leave simultaneously, or there is one more possible, theoretically possible possibility is there. What could be that possibility? Yeah, Mohammed, tell me. Suppose if the leaving group comes out before the new group arrives, right?
Yes, sir.
A leaving group slowly start breaking away from the substrate. Okay. On its own. It may appear that it is on its own, but there are some factors which are helping the leaving group to come out. Okay. So, but as of now, we will think that the leaving group which was sitting inside the substrate that start breaking on its own slowly. Okay. So what happened? And this is going to be a slow step, and it is known as RDS. What does this mean?
It's a rate determining step.
Yeah, rate determining step. So all the factors which are important for this step will affect the rate. Okay. And what happens if this the leaving group comes out? The leaving group comes out as Br minus, and there is a carbocation formed, carbocation intermediate. Formed during the reaction, right? So now is it possible for the nucleophile to go and attack? Is it possible?
Yes, sir.
Yeah. Why it is possible? We actually initially have not let the nucleophile come and join because it was too bulky. But here we are saying that okay, it is very fast. Okay, it means it is happening very quickly. But where that all that bulk and steric hindrance has gone now? Yeah. Yeah, Vamsi. Mohammed, would you like to add something? Yeah. Now we will not think of that bulk and all, because first of all, there are only 3 groups present. And another thing is that after the departure of leaving group, this carbon has acquired a plus charge. It is a carbocation, right? And the carbocation is flat. It is sp2 hybridized, and there is an empty p orbital. Okay. There is an empty p orbital which is perpendicular to the plane of this carbocation. Okay. Right. So now because it is flat, earlier it was not flat. Look here. It was, what was the geometry of this carbon? Mohammed and Vamsi, tell me.
It's a tetrahedral.
Yeah, it was tetrahedral, and the 4 groups were there. So direct attack of nucleophile, the carbon was not accessible to the nucleophile, but slowly the leaving group came out along with the electron pair, leaving behind a carbocation. The carbocation actually it has changed its sp2 hybridized. It is flat. Okay, and now there is lot of space available for the attack of the nucleophile. The nucleophile can come and join from both the sides. It is trigonal planar, right? The nucleophile come and share its lone pair, and this is going to be an easy step because there is a bond formation. Okay, right? And it can happen very quickly. And finally, because the water is the nucleophile and it has O plus, it will become neutral by the by removing its H plus. The H plus will be taken away. Okay, this is just a simple step, not the part of the main step. The main step are these two. Okay, these two steps are the main steps. So first step is departure of leaving group, followed by attack of nucleophile, right?
Yes, sir.
Clear? So this leads to the formation of a product, and this is the energy profile. So you have alkyl halide, okay, and this is a difficult step. As you can see over here, the height is, this is the activation energy, it is too high, very high. Okay, and here you will end up with an intermediate known as carbocation intermediate. Okay, this is an intermediate, and this is known as, this hump is known as transition state. So how the transition state will look like? So here you are having Rx and this is R plus, X minus came out. Okay, so if someone asks you how the in between it will look like, it will look like this. You will observe that the X minus is slowly coming out and the R plus is forming, right? The partial charge is appearing on the R. Is it clear?
Yes, sir.
Okay. And R plus, and there is a attack of water or the nucleophile, which is an easy step. And how you know it is an easy step? From the graph, can you tell me it is an easy step? Which thing can let you decide that the second step is going to be very easy? Okay, you can compare the levels. Okay, the cation is the second hump is not going to be that high, right? So the energy required for crossing that second step, which is this one, is very less, and it can happen very quickly, right?
Yes, sir.
So that's how the product formed. Okay, this is the mechanism of SN1, right? So it is a first order reaction. Why it is first order, or why it is unimolecular? First of all, tell me SN1. SN1 means substitution nucleophilic unimolecular. Why it is unimolecular? There are two species already involved in the reaction, but why it is called unimolecular? Any idea? Yeah, Mohammed, tell me. If there are two things which are involved, why it is called unimolecular? There are two molecules. Yeah, Vamsi.
So reaction happens one by one separately. With
Yeah,
one
yeah, yeah. Molecularity is the number of molecules, not the total molecules which are there in the chemical equation. No. Molecularity of a reaction is actually the number of molecule in the slowest step, the difficult step. Okay. You break all the reaction in single step. Okay. Step by step you write, and you check how many molecules are involved in the most difficult step. Okay, this is the rate determining step, or most difficult step, which is actually the cleavage of leaving group. Okay, and if you look here, only one molecule, one substrate molecule was involved. Unlike SN2, only one molecule is involved. SN2, two molecules were colliding, the nucleophile was colliding with the substrate molecule, and that resulted into the reaction. But in this case, only one molecule is involved. Okay, that's why it is called unimolecular. SN1. Okay, unimolecular reaction. The other thing is, uh, the, because in SN2 there were two species involved, the rate dependent, the rate was depending upon the concentration of both the species. Okay, because if you increase the concentration of both the species, the reaction is going to increase, its speed is going to increase, because if more concentration means more collision, they are going to collide more frequently. If there is more collision, you can increase the rate by increasing the concentration of nucleophile, or by increasing the concentration of substrate, or by both. That's what we have seen. So rate was K times the concentration of substrate into concentration of nucleophile. But that has not happened in SN1. In SN1, this highlighted box. This is the main reaction. Okay, this is the most difficult step, as you can see over here. Okay, so everything is dependent upon this. Okay, this is the main climax of the reaction. So rate of the reaction, or the speed of the reaction, Mohammed, that is equal to K times the concentration of the substrate. Okay, substrate is this one. Right? It is first order reaction. Okay, clear?
Yes, sir.
So other thing, so this is the rate law. Rate law is the actual equation which tells us how the rate is dependent upon the concentration of the various species which are mentioned in the chemical reaction. Reaction may have many species, okay, but overall reaction doesn't give us the exact picture of the sequence of steps which are happening. That is just the algebraic sum of the whole sequence of steps. Okay, that is not going to give us the exact picture. The exact picture will be given by the mechanism which is written over here. Okay, this is unimolecular mechanism. Okay, and the rate determining step involves the formation of a carbocation and the departure of leaving group. Both take place simultaneously. So rate of reaction, and that involved only one thing, the substrate itself. Okay, so rate of the reaction dependent only on the concentration of the alkyl halide. Is it clear?
Yes, sir.
So what will happen if you increase the concentration of, what will happen if you increase the concentration of nucleophile? If you double the concentration of nucleophile, how the rate is going to get affected?
So it will not affect.
Yeah, it will not get affected. It is because the rate of SN1, you can write, Mohammed Vamsi, the rate of SN1 is independent of the concentration and the strength of the nucleophile. Okay, it is independent of the concentration and strength of the nucleophile. Is it clear?
Yes, sir.
Because nucleophile, attack of nucleophile is already a easy step. Okay, that is not the thing which is happening very slowly, so that will not affect the rate of SN1. So which is the other factor which will affect? The main factor, you need to look for the rate, you need to look at the substrate itself, because in the RDS the substrate is actually, only the substrate is participating, and it is breaking away into two, the leaving group and the carbocation. So can you say something about the nature of the leaving group? Can you say something about the alkyl group which will increase the rate of SN1? Any idea? Vamsi, Mohammed, tell me quickly. Yeah. What kind of substrate you need to take, or what kind of leaving group you need to take, that will make SN1 happen more quickly? Yeah. Vamsi, any idea?
So I didn't get the question, sir.
Actually, the rate of SN1, how it is dependent upon the nature of the substrate. Clear?
Yes, sir.
So what kind of substrate you need to take that will make SN1 easier or faster?
So more substituted. I mean, which has more alkyl groups.
Yeah, that is one of the point. Good. Mohammed, would you like to add something? You need to take a substrate which can form a stable carbocation. Okay. That is a more general statement. So rate of SN1, you can write this one, is directly proportional to the stability of the carbocation. Okay. Why? Because the carbocation is forming in the main step, which is most difficult. Suppose if the carbocation formed is 1 degree. 1 degree means primary. It is only having one alkyl group. And if the carbocation is 2 degree, it is having two alkyl group which are bit more electron donating and which will tend to stabilize the carbocation. Okay. And if you have tertiary alkyl group, it is going to form carbocation very quickly. Okay. Because the tertiary alkyl group has 3 alkyl groups and it is stabilized by the carbocation is stabilized by hyperconjugation. It has 9 alpha hydrogens, inductive effect. The carbocation can form very easily. Okay. So you can look at the energy profile. Which reaction is going to be the most difficult and which reaction is going to be the most easiest one? This is going to be the most easiest one. Okay. So
Yes, sir.
tertiary carbocations are the most stable carbocations. Okay. And they can form very quickly, and that will increase the rate of our SN1. Okay. Nucleophile has no role because nucleophile is appearing after the main step has already happened. Okay. So you need to concentrate in order to check the rate or the speed. You need to concentrate on the main step, right? That is the attack of the, that is the departure of leaving group and formation of a carbocation, right? You need to look at the stability of the carbocation. Okay. But not only tertiary, there are other type of carbocations also which are very stable, like benzylic, right? What
Yes,
do you
sir.
mean by benzylic? And why it can form a stable carbocation? Yeah, any idea?
So the halogen is attached to a carbon which is further attached to one benzene group. I mean aromatic group.
Yeah, good. Actually, this carbocation, this is benzylic carbocation. It is stabilized by resonance. Suppose if the leaving group comes out and there is a plus charge on the carbon, this plus charge will be taken care of by the double bonds. Okay, it will pull the electron of the double bond actually are loose. Okay, and the double bond electrons can pi electrons which are loose can come and join, can come out of the benzene. Okay, but that doesn't mean you can put any electron anywhere. Okay, the pi bond was like this, it was in the benzene. Okay, it was like this in the benzene ring, and they moved like this. Okay, they shifted on other side. Okay, and that will neutralize the plus charge on this. It will come over here. There is no charge which is there on this carbon because it is now also making 4 bonds. Okay, and this is a plus charge will attract the double bond from The pi bond which is ahead of it, it can come this side. Okay. It can move ahead also, right? So what this phenomena is known as? Yeah, Vamsi.
Say resonance.
Yeah, resonance or hype, or it is mesomeric effect. Okay. So benzylic carbocation can, so actually structure is not any one of them. It is the average of all these structure, because the electron will not move one by one. Okay. So, okay. They will, actually it is a cloud, electron cloud. We know that the electron have wave nature, right? So this bond will acquire double bond character. The plus charge which was formed by the departure of leaving group is now not completely plus, because if you take the average, this plus charge has appeared at this position, this ortho, para, ortho positions. Okay, due to which these positions have also acquired some charges. Is it clear?
Yes, sir.
Mohammed, can you hear me? Right? So this can form very quickly. Benzylic carbocation. Not only benzylic, the other carbocations like this is known as allylic halide. Allylic. Okay. This is also in a same way stabilized by resonance. So allylic carbocation can, if it forms, it can be stabilized by resonance. Why? Because there is a pi electron cloud, and the pi electrons are very easily they can be moved. Okay, because their electrons are above and below the bond, not between the two atoms. Okay, they can move, shift very easily. Okay, so this allylic carbocation, allylic substrates, benzylic substrate, they can form a very stable carbocations. Okay, and thus they can undergo SN1 reaction very easily, and they can also undergo SN2 reaction also, because SN2 actually this double bonds will stabilize the transition state. But SN1 also very easily, because the carbocation is stabilized. Is it clear?
Yes, sir.
Okay. So if I ask you to compare the rate of SN2 reaction, not SN2, SN1 reaction, for the following substrates. Okay. What's going to be the order of the rate of these substrates? Decreasing order of rate of SN2. Yeah, decreasing order of rate of SN1 reaction. So you need to check the leaving group. Which is the leaving group in all the cases?
BR.
Yeah, BR is same, right? Just so Br is same in all the cases, right? So what is changing then? What is changing and how it is going to affect the rate of SN1? Yeah,
So the carbocation.
the carbocation. You need to check the stability of the carbocation, right?
Yes, sir.
So where it is going to be most stable and where it is going to be least stable?
So in third, it will be more stable, and
Yeah, in third it will be the most stable because actually it is 2 benzene. The other pH is actually the second benzene ring, okay? Right?
yes, sir.
So the feature which we discussed in the benzylic carbocation, it is available on 2 sites, okay? So this carbocation which is formed is delocalized on at 7 positions. Okay, 7 positions you can see over here, right?
Yes, sir.
Because in all the rings it is going to come at the ortho and para positions, okay? So it will become very stable. It is divided now. So charge if it is divided, you must have studied in your electrostat that its electrostatic potential energy is going to come down. So it is going to be very stable. So third is going to be the fastest, yeah, followed by
Fourth.
yeah, fourth, right? After that,
Second.
second, yeah. And after that, first. First is going to be very, very, very less reactive. Why? It will not undergo, it will not undergo SN1 reaction. What is the reason?
Sir, it is not a stable carbocation. It will not form a stable carbocation.
Yeah, it will not form a stable carbocation, and any other reason? Yeah. So carbocation will form if the leaving group comes out of, but in this case the leaving group doesn't want to come out. Why?
So because it's highly stable.
Actually, the leaving group has unpaired electrons, lone pairs, and those lone pairs are just adjacent to the pi electrons of the benzene ring. Okay, so or I can draw an orbital picture which will look like this. Okay, these are the lone pair of the bromine and these are the pi electrons of the benzene. Okay, so pi electrons are already adjacent to one another. They are actually overlap together, and that's how they are moving throughout the ring. That has caused stability. This is the phenomena of resonance. And the Br lone pair is also very adjacent. That can also come and join these pi electron densities. So it is a resonance. Okay. Or if you want to depict it one by one, you can show it that the lone pair of the bromine is going to get into the ring. Okay. And the pi electron is going to get shifted because this carbon is already making 4 bond. It will not make 5 bond. So I need to shift the pi bond aside. Okay, the minus will come. The minus will go and shift. That's how you can show. Okay. So in this whole process, the carbon bromine bond has acquired partial double bond character. Right? I hope both of you agree, Krishna and Mohammed.
Yes, sir.
Okay. So it has formed a double bond character and that's why it is not going to come out. Right? So vinylic halides and aryl halides will not undergo SN2 or SN1 reaction. Why? Because they have a double bond character between the carbon and the halogen group, okay, due to resonance, right? And there is one more thing which you will notice, that SN1 reactions are also known as solvolysis, okay. Why? Because the nucleophile is none other than the solvent molecule itself. You dissolve the substrate in a solvent, that solvent molecule, one of the solvent molecule come and join to the carbocation which is formed in SN1 reaction. So nucleophile is same as that of the solvent, okay, molecule. So water and alcohol. So it is a reaction with the solvent. That's why it is known as, or the breaking with the help of solvent. So it is also known as solvolysis. SN1 reactions are known as solvolysis reactions, okay. So in this case, you can see the methanol, it is dissolved in methanol, and methanol is also, so initially this slowly, and this Br minus broke away from the carbocation, and this methanol has once, not directly like SN2, okay, you need to form a carbocation first, okay, then you need to show that the methanol is going to come and attack, the lone pair of oxygen is going to come and join to the carbocation, okay. Is it clear? Right? So solvent plays a very crucial role. The leaving group should be a good leaving group. If it is a poor leaving group, then definitely SN1 can't happen. The carbocation which is forming should be more stable. You should not have a substrate like methyl which can't form a stable carbocation. So not everyone can have SN1 reaction, okay. Benzylic, tertiary, okay. So SN1, SN2, this thing is mutually exclusive. So SN2 was happening at the places or the on the substrates where there was no other alkyl groups connected, which were very small, okay, because that actually a lot of crowding was there in the transition state. But in SN1 reactions, the whole thing has changed. So in SN1 reaction, actually the leaving group was coming out on its own, leaving behind a carbocation. So we need more alkyl group, more branching, or the pH groups attached to the carbocation that can stabilize the carbocation by resonance or by electron donation, okay. So if you have a more branch substrate or a substrate which can form a stable carbocation, then SN1. But if you have a less branch substrate, then SN2, right? Clear?
Yes, sir.
And just first step, we discussed that this Br slowly breaks away from the substrate. But I told you that this is not happening on its own. There is someone else who is helping them out. And who is helping them out to break away from one another? Who is helping them out? Yeah. Can you tell me? Mohammed and Krishna. Who is playing a role? Who is helping them out to separate away from one another?
It's a
Yes.
catalyst.
No, not the catalyst. Actually, it is the solvent molecule itself, right? So solvent molecule itself is helping them to break away from one another. Okay, how come solvent can help, and what kind of solvent do I need for SN1 reactions? Okay, that you need to discuss. Okay. Yeah, any idea about the types of solvent? Yeah, there are two categories of solvent. Actually, you can have many categories. Okay. So, like polar and non-polar, that you might be aware of.
Yes, sir.
Okay. And in polar, you have two categories. One is polar protic, like water, like methanol, this is protic solvent. And the name is very clear. Protic means proton, means H is directly connected to oxygen. Okay. And why do I need this kind of solvent for SN1? So SN1 reaction can happen very quickly in Protic solvent. Is it clear? Protic.
Yes.
And there are other solvents just like acetone or propanone, or similar to acetone is this DMSO, where you have sulfur in place of carbon, dimethyl sulfoxide, and this is DMF. These are aprotic solvents because there are hydrogens, but they are not connected to oxygen. You can see. Okay. So SN1 reaction can happen very easily with Protic solvents. Okay. Because the Protic solvent, as you can see over here, this Protic solvent has positive charge on H. It is the water is the most common Protic solvent, and it has a negative charge on oxygen because of the electronegativity difference. Okay. So it can help the cation and anion, both of them, to stabilize very well. How? Suppose if the leaving group is actually minus. Okay, you can see over here. So once it comes out, actually it doesn't. Why it will come out? Why a bond will break? Right? That's the question. Okay, because the bond should not break on its own. Then bond actually don't break on their own. So why they are breaking? Actually, someone must be helping them to break away. Okay. And who is that someone? That is a solvent. And what kind of solvent do you need? You need polar Protic solvent. So what are Protic solvent? Protic solvent has H directly connected to oxygen, and that's why they have a plus charge on H and minus charge on oxygen. Okay, and we need both type of charges in SN1 because there is a carbocation which is forming and there is a leaving group which is coming out. Okay, so you need a solvent which can furnish both type of charges. Okay, suppose if the plus charge is there, the plus charges will come and surround, will form a layer of plus charges around the leaving group. So in a way it's good. Why? Otherwise what will happen is, why this leaving group will stay away from plus charge? It will get connected back to, it will get attracted back and it will come and join back this come and join this carbocation back. Is it clear?
Yes, sir.
And not only this leaving group which is stabilized, this carbocation is also stabilized. How come? The carbocation has plus charge, and carbocation plays a very crucial role because until unless it forms, the reaction will not proceed ahead. So we need to do something to stabilize the carbocation. And what we can do, we can take a polar Protic solvent. That's the most easiest way. And how a polar Protic solvent can help a carbocation to form easily, because carbocation has plus charge. Okay. And this polar Protic solvent has plus as well as minus charge. Okay. And the negative charge will come and form a layer of solvent around the carbocation. Okay. So you can see this kind of, this is known as solvation. And that's why NaCl is soluble in water. You might have studied in your class 11th also, hydration enthalpies. Okay. So this plus charge is there, you can see, right? And this plus charge is stabilized by water molecule with the O facing the plus charge, oxygen atom facing, because oxygen atom carries the negative charge. Okay. Not only the carbocation which is stabilized, the leaving group is also stabilized. The leaving group is minus, or it is electron rich, and the water molecule will surround the form a layer of solvent around the leaving group with H plus facing the leaving group, and that because H plus will get attracted towards the minus charge of the leaving group. Okay, the leaving group will also be stable, and if both are stable, they will separate very quickly. And if they will separate very quickly, it was the step which was happening with the most difficulty. Okay, so our SN1 will happen very quickly. Okay, so what are the ideal solvent for SN1 reaction? What kind of solvent do you require? Polar Protic solvent, right? So if someone asks you rate of SN1, Okay, this is a very famous question. Is it going to be faster in alcohol? Is it going to be faster in the methanol? Or is it going to be faster in dimethyl ether? How the rate of SN1 is going to get affected in these three solvents? You have kept the leaving group, you have kept everything else same, the substrate same, okay, everything same. But how the rate of SN2 will change if you change these solvent, okay? The answer is this is going to be the fastest, because water is a very good solvent. It is very polar solvent, but that was not sufficient. You need to tell more detail. Okay, water has H plus. It is a polar protic solvent, and there are two on both the sides. It has H plus. It is more polar. Okay. On the other hand, methanol has only one side. You have a carbon group, which is not as polar as hydrogen. Only one side you have hydrogen, which is having a plus charge. And oxygen is having a minus charge, and what will the plus charge and minus charge, both I need them. I need both of them to stabilize cation and leaving group. Okay. But what happened to dimethyl ether? No, it is not going to. It is not a suitable solvent for SN1 reaction, because there is minus charge, but the plus charge is not there on H plus. It may be somewhere in the on the carbon, but it is of no use because carbon is not exposed. Okay, it is actually CS3, so it is of no use. So only minus charge is there. So you can't, if this leaving group comes out in aprotic solvent. Aprotic means the solvent which doesn't have proton connected to oxygen or electronegative atom. This X minus, if it comes out in aprotic solvent, imagine what will happen if you put it in a sea of negative charges. This X minus is already very negative, and if we put it in a solvent which is already having a negative charge, the plus charge is actually not exposed. So this minus will become too unstable to stay away from the substrate. It will go and get back to the substrate, and it will join back. Okay. So that's how solvent plays a very important role. But in SN2 reaction, we require a different kind of solvent. We don't want polar protic solvent. We want aprotic solvent. We do not want plus charge. Okay. Why? Because SN2 reaction, actually, how do they happen? Actually, they do not break on their own, first of all. Actually, in SN2, if you consider CS3, we have the nucleophile is playing a proactive role. It is coming and attacking on the carbon, and that is leading to SN2 reaction. But suppose if you have protic solvent which can stabilize the minus charge as well as plus charge, what will happen? This nucleophile will be covered by the H plus, okay, of the polar protic solvent. And if it is covered, then this nucleophile, why it will go and attack? If it is already covered by the H plus around itself, the solvent will form a layer envelope around it. So it will not go and attack. So rate of SN2 is not, are not favored. SN2 reactions are not favored in protic solvents. Okay, SN2 reaction are favored in aprotic solvents like this. They have a negative charge. The plus charge is there, but it is of no use because it is inside. So you can think that it is a negative charge. Look here. Okay, so it is a sea of negative charges. So what will happen to the nucleophile? If you put nucleophile in the sea of negative charges, it will become more activated because wherever it is going, it is feeling repulsion. So now where the nucleophile will go? It will go attack on the substrate. That's how the SN2 reactions. That's how the polar aprotic solvent favor SN2 reactions, while protic solvent favor SN1 reaction. Is it clear?
Yes, sir.
Okay, the other thing is stereochemistry of SN2 and SN1 reaction. So what was happening? Can you tell me in one word? Suppose if you took a chiral substrate, what happened to the carbon atom bearing the leaving group, and which after the completion of reaction was attached to a nucleophile? What happened to it? Yeah, tell me. Actually, remember, actually both were taking place simultaneously. So actually there was an inversion happened, right? Remember?
Yes, sir.
An inversion, because if there are already one guest already sitting and there are another guest who need to come and the guest are leaving, it is better for us to have two different doors. Okay. So the nucleophile was coming from this side and the leaving group was going from this side. Okay. So finally, what you observe, you observe that the nucleophile come and join from the side opposite to the leaving group. Okay, right. So inversion happened. That was known as Walden inversion, and we have seen Walden inversion. Somewhere a lot of examples I took. Look, so I attached I from the back side. I attached the BR was above the plane, and I attached the OH from behind the plane. The BR was pointing above and I attached the leaving group ACT from behind the plane. Okay, right. So that's how the reaction has happened, right? But in SN1, if someone asks you what is the stereochemistry, what you can say? For SN2, you can say just one word: inversion will take place. For SN1, what can you say? Yeah, Mohammed Kamsi. Yeah, for SN1, you need to say racemization will occur. Right? Or racemic mixture will form. If there is a chiral carbon which is connected to four different groups, then only you will observe this phenomena. If the carbon is not chiral, it is just a simple carbon which is not having four different groups, then it is not a matter of concern. Okay. This inversion and this racemization is going to happen only if you have the chiral carbon which or the wherever the leaving group is connected, it should be chiral. Then only you need to discuss these things. Okay. So what happens is, I told you that the carbocation is formed and the what is the geometry of the carbocation? It was, what was the geometry in hybridization? It was trigonal planar, right?
Yes, sir.
With a p orbital, empty p orbital above and below the plane of the molecule. And if, because leaving group has already gone, now only the three groups are there with a empty p orbital, right? So from which side the nucleophile is going to come and join? Tell me. Where the nucleophile can come and join? From which side? Because this is a flat molecule, the nucleophile can come and join from the both the sides with equal probability. Clear?
Yes, sir.
So racemic mixture is going to form. Racemization is going to occur. Okay. You can see over here the racemic mixture. Racemic mixture means what? What do you understand by racemic mixture? Means if there is a chiral carbon, the OH minus is going to get, so look, Br is coming above the plane. So the OH is going to join from the side which is on the side which is same as that of the Br leaving group, and also the OH minus is going to join from the side which is actually opposite to the Br. So both will form in equal amount, 50-50. Okay. So both will form the same configuration because the leaving group has already gone. Now you have a flat cation. A nucleophile can come and join from both the sides with equal probability. Okay, that's why you have a racemic mixture or enantiomeric pairs of enantiomer or two mirror images will form. Okay. And both SN1 and SN2 are affected by the nature of the leaving group. Because leaving group was coming out, it need leaving group should be a good leaving group, then only it will come out. Okay, either in SN1 or SN2. In both the cases, the one common thing was the leaving group should be a good leaving group, and if you take a good leaving group, the rate of SN1 is going to increase, or SN2 is also going to increase. Okay, so these are the general differences and similarities between the SN2. SN2 is a one-step reaction. SN1 was mainly two steps. Okay, there can be more than two steps. Just I'm talking about the main steps. Okay, the departure of leaving group leading to the formation of cation and attack of nucleophile. Right. So SN1 is two main steps are there, but actual number of steps can be three. Right, just like removal of H plus from water. Okay, but there are too many steps. So it was in SN2, it was a bimolecular mechanism. Okay, single step, and that bimolecular step which involved nucleophile and substrate was rate determining step, RDS. And SN1, the RDS was the departure of leaving group. It has only one molecule involved, the substrate molecule. Okay, and that is a unimolecular. Okay, so rate is controlled by steric hindrance because everything was happening in the same step. It was very bulky, but in SN1 rate is controlled by the stability of the carbocation. Okay, that you need to consider first. So methyl halide, primary, secondary alkyl halide undergo SN2, but not the tertiary alkyl halide because it is too bulky, too crowded, and the nucleophile will not be able to access the carbon atom. But in this case, the tertiary alkyl halide is going to react with much more ease because it can form a stable carbocation. And if the carbocation is stable, the energy is lower. Energy is lower means it can form very easily, right? The product has inverted configuration because the nucleophile has to come and attack from the back side because the leaving group is still there. Okay, and that led to the inverted product having inverted configuration, which was known as Walden inversion. But in this case, in SN1 reaction, both the products are formed because the leaving group has already gone out. There is a carbocation, both, and the nucleophile can come and join itself to the substrate from any of the sites. So from both the sides with equal probability. Okay, that's why the respiration has occurred. And leaving group tendency, yeah, that is same because leaving group has to come out. If you have SN1 or SN2, in both of them the leaving group has to come out. Okay, then only if you take a group which is very reluctant to come out, that neither SN1 is going to happen nor SN2 is going to happen. None of them. Why alkanes are not substituted by any other group? Okay, because they do not have any polar group. Okay, they do not have any group which can come out easily. So alkanes will not undergo SN2 or SN1. Okay, they are good. They are inert. That's why they are known as paraffins. Okay, little affinity. Okay, right. And the better the nucleophile, the faster is going to be the rate of reaction. Nucleophile affect the SN2 reaction in two ways. Okay, stronger nucleophile, faster rate of SN2, and nucleophile concentration term was appearing in the rate equation. So nucleophile concentration, if you are going to double, the rate is also going to get doubled. So nucleophile affect the SN2 reaction in two ways: by its strength, by its concentration. Okay, but in SN1 reaction, nucleophile has no role. Okay, because SN1 reaction, the nucleophile was already appearing in the step which was very easy step. The nucleophile has to just come and join itself to the carbocation. And that was not a difficult step. That is not the step which is going to control the rate of the reaction. So neither the strength of the nucleophile nor the concentration of nucleophile is going to affect the rate of SN1 reaction. Is it clear? Right. So let's discuss some of the reactions which are related to SN1 or SN2, and also they are useful for the preparation of alkyl halides from alcohol. So this reaction which I'm going to discuss, it is there in two chapters. Okay, in alkyl halide, because I can prepare alkyl halide from alcohols by this reaction. Okay, and this reaction, same reaction you will find in alcohol chapter also, because alcohol can react with HX or HCl, HBr, HI and give alkyl halide. And this is a very famous reaction which is also applied to test the type of alcohol. Okay, so this is going to be SN1 reaction. Okay, this is the catalyst. right? And how it has happened? What could be the, so suppose if I want to put Br or Cl, do I need to take NaCl, simply NaCl, or HCl? Yeah, just tell me. Or both, which can lead to the formation of RCl. Yeah, tell me. Yeah, Krishna. Mohammed. Where
In the
the,
first case.
yeah, in the first case, this one,
Yes, sir.
no, this will not happen. Okay, why it will not happen? Though everybody can write the equation, everybody can write the equation and can say, okay, we have written the equation, okay, this should form, okay, the equation is correct. But my dear students, who is going to come out? Just think of it, the OH minus is will be coming out. Okay, NaOH is a very strong base. It is very unstable, it is very reactive. Cl minus is very stable. We know. We eat a lot of salt in our food. We put a lot of salt in our food. Okay. So Cl minus doesn't harm us. NaOH is very strong. It can't. It is a very, very unstable compound. It is very strong nucleophile. So how can you expect a stable chloride ion to come and push away a group which is very unstable, which is a very strong base? Can it happen? Mohammed and Mamsi, tell me. Can it happen?
Awesome.
No, it can't happen. You can write strong bases are poor living groups. They are unstable. They have high energy. They are strong. They are very reactive. And if they are reactive, why they are going to come out and sit ideal? It cannot happen. This is actually ROH. Okay. So the second reaction can happen. And remember one thing, one thumb rule, it will be useful everywhere in all the subsequent chapter. And that rule is, if you want to remove OH, if you want OH to come out, you need to take acid. You need to take H plus. Why? Why am I saying like this? If you want to remove OH from a compound, you must have acidic medium. Why? Vamsi and Mohammed, tell me. Okay, because acidic medium, first of all, acids will give H plus. That is quite obvious. H plus doesn't have any electron, and it can come and join itself to the lone pair of oxygen by taking the lone pair, right? Is it clear,
Yes, sir.
Vamsi? So what it has become? Okay. What it has become? Oxonium ion. Okay.
Yes,
And
sir.
so earlier we were ruling out the separation of OH minus. But now if it after proton, this step is known as protonation of OH. It happens in acidic medium. And once the OH is protonated, now tell me which group will come out. And will it come out or not? Yeah. If we have OH2 plus, it is more polar, right? And if it comes out, it pulls away the bonded electron with itself, okay? And it comes out as neutral water. So can this group come out?
Yes,
Is
sir.
the yeah, it can come out very easily. Okay, is the condition now more favorable as compared to the condition in which we were removing the OH minus? Yeah, they are very much favorable now. Okay, because OH minus can't come out easily. So what you did, you took acid that protonated the OH minus, and the leaving group is water. Water is a very good leaving group. Okay, it can come out very easily because it is a weak base. Weak bases are good leaving group. Just write the thumb rule. Okay, weak bases. Water is a weak base. That's why we are able to drink it, but we can't drink NaOH. We can't even touch NaOH. Okay, it is very, very risky. Are good leaving group, and it can come out on its own, right?
Yes,
And
sir.
if it can come out on its own, what is left behind? A carbocation, right?
Yes, sir.
Means this is which kind of mechanism? This is SN1. But the leaving group actually was not readily a leaving group. It was not ready to leave, but you took acid, and that acid, due to that acid, it has undergone some changes. And what are those changes? Protonation has occurred. And after protonation, it became a good leaving group, right? And it came out
Yes, sir.
very easily, leaving behind a carbocation. So reaction with HX, what will be the order of rate? Yeah, tell me. What will be the order of rate of reaction with HCl of alcohol? The fastest one is going to be the methanol or the tertiary ethanol, which is going to be the fastest. Yeah, Vamsi, tell me.
So methanol.
Methanol, you need to look at the
No, so it's
mechanism.
tertiary methanol.
Yeah, because it is SN1. Yeah, exactly. It is tertiary. Methanol is going to be very difficult. Tertiary alcohol are going to react with HCl, HBr, and HI very, very quickly. Very, very quickly. Okay. Right?
Yes, sir.
So this is actually known as, so ZnCl2 is also taken because that acts as a catalyst. It helps the OH minus to come out, and otherwise the H plus is very much required. So you have HCl available in the lab. So if you need to make chloride from alcohol, you can write just HCl. That's it. So all the labs have HCl. That is the most common acid, okay, which are there in all the labs. But you don't have HBr, okay, because it is gaseous, it can get oxidized. So if HBr is not there, you can do the same reaction with HBr and you will get bromine. Okay, that's the one thing. But HBr is not available in the lab. So what you are going to do? Tell me. If HBr is not there in the lab, can you take simply NABr without H2SO4?
No,
Can you
sir.
see? No, because if you would have taken NABr simply, the who is going to come out, the OH minus is going to come out. NaOH will form. Is OH minus ready to leave? No. It is a strong base. So what you need to take, HBr was not there in the lab, you took some acid, H2SO4. H2SO4 gave its H plus for both, for HBr, right, or for ROS to get protonated. And this protonation made, acidic medium made OH a good leaving group. It came out, but by the same mechanism, it formed a carbocation, okay, and that carbocation was attacked by Br minus. Now Br minus can come and join, and that's how it has happened. Is it clear or not?
Yes, sir.
Okay, very good. So just answer this question quickly. We are running out of time. So what is going to be the answer for this? Yeah. Which OH should I replace by Cl? Is it the upper OH or the lower or both? HCl is going to give its H plus and to the OH, and the OH minus will come out as water, leaving behind a carbocation. The carbocation will be, this is SN1 mechanism. Yeah, tell me quickly.
Then the one which is attached to CH2.
Yeah, very good. Why, Mohammed? This will not be displaced. Why?
So because of SN1 reaction.
Yeah, SN1 reaction, and one more thing which I told you just now. This OH has lone pair. This is already involved in the resonance with the benzene, and there is a double bond character. And if there is a double bond character, it is very difficult for us to pull out that group. Okay,
Yes, sir.
so it is not going to happen. It is going to happen in this way, right? So we will discuss it more on the next time. Let's do it on the next one. But this is a very, very important reaction for 2 chapters. Okay, for the next chapter also. Okay, so let me end today's class. Hope you enjoyed the class. Okay, bye. Good night.
Thank